talk about the mean value theorem. And there's a couple of things. There's one thing that I forgot to mention last time, and that's the extreme value theorem. And if f is continuous on a closed interval, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers in the interval. Now these numbers could be endpoints. If f is, these numbers are, these values are going to be attained at either endpoints or where f is a critical number. Okay, so either critical numbers or endpoints. We talked about critical numbers last time. That's where the derivative is 0 or doesn't exist. But it will obtain an absolute maximum and an absolute minimum. Okay, so now that's the extreme value theorem. Now today we're talking about the mean value theorem, and the precursor to that is Rolle's theorem. And it's really similar to the mean value theorem, except it has this third condition, which the mean value theorem only has these first two. But okay, so if f is continuous on a closed interval and differentiable on the open interval, and the values at the endpoints are equal, then there is a number c such that f prime of c equals 0. Okay, so let me try to draw a few pictures of try to illustrate how this works. So you have some function from a to b. This is on this interval. So it could be, maybe it's like this. Maybe it goes up like that. Okay, but these values are the same. Or maybe it's like, or maybe it could be some function, you know, a different function could be like this, where it starts up here, but then ends up at the same place. But the point is that these values are both the same. These y values at a and b are the same. Okay, here they're both 0, but here they're maybe like something greater than 0. Okay, so what Rolle's theorem says is that there's going to be some point in here where the derivative is 0. Now for this function, maybe if this is the highest point on the graph, then it's going to have a horizontal tangent right there. And so then the derivative will be 0 there. Okay, now for the red function, maybe right here is the highest point on the graph, and here's the lowest point. And so in that case, you have two different values that satisfy the thing. Okay, there could be more than one value c that satisfies the derivative is 0, but where it has these horizontal tangents, the derivative is going to be 0. And that's pretty much how you prove it. Okay, so part of the proof involves the extreme value theorem. And essentially, let me just give you an idea. That's just the gist of the proof. So it goes something like this. First of all, you consider case 1, where f of x is just a constant, which is constant. And in that case, if you just have, and it's just going to be a horizontal line, right? And in that case, the derivative is 0 for all x's in the interval from a to b. Okay, the derivative is going to be 0. So we're done, you know, because we found at least one value, you know. Let's take at least one value, just take the midpoint. Derivative is 0 at the midpoint. So and c can be the midpoint, and there you go, you're done. Okay, so check mark, done. Case 2 would be, if this is not true, then you're either going to have, there exists an x in the interval such that f of x is greater than a, or there exists an x such that f of x is less than, not a. What am I thinking? Other than f of a. Or there's going to be a value that's less than f of a. Okay? So you're going to have, either going to have a, unless it's constant, if it's not constant, that means there has to either be at least one value that's greater than f of a, or a value that's less than f of a, okay? Because f of a is a value there. So so you either have that, or maybe even both. In this red case, you have both. There's values over here that are greater than, and then there's values over here that are less than. The green one, it's only this one right here. There's values that are greater than f of a. All the values are greater than f of a except f of b. So let me just go into. So from here, what you would argue is that there is an absolute maximum. Okay, so we'll call this EVT, extreme value theorem. F has an absolute maximum. Okay, and that absolute maximum is going to be in the interval. Okay. In the open interval. And the derivative has to be 0. Okay, because it has to be a critical number. Has to be a critical number. Okay, so we said that the local maximums and minimums, it has to be a local maximum, which means that it has to be a critical number, which means that the derivative has to be 0. Okay, because critical number means that the derivative is 0 or the derivative does not exist, right? But f is differentiable. Okay, so that knocks that out. That makes that not a possibility. That means it has to be this one. Okay, which is the conclusion of Rolle's theorem. Okay, so enough with that. Let's look at exercise number 1. Verify that this function satisfies the 3 hypotheses of Rolle's theorem on this interval. Okay, so number 1, it's continuous. Okay, it's a trigonometric function, and it's continuous where on its domain, so it's continuous, and it's continuous this is continuous everywhere. Okay, number 2, it's differentiable. Have cosine of x over 2. I mean, you don't necessarily to show that something's to show that something is differentiable, you don't necessarily have to find the derivative. Okay, but if you can find the derivative, then great. That's what the derivative is on this entire interval, everywhere. So that's differentiable. And number 3, f of pi over 2 is sine of pi over 4. So I put a pi over 2 in for x, that's pi over 4, which is 1 over root 2. F of 3 pi over 2 is sine of 3 pi over 4, which is also 1 over root 2. Okay, so this angle, pi over 4, is right there. And the sine is opposite over adjacent. I mean, opposite over hypotenuse. This angle here, 3 pi over 4, is right there. And it's also opposite over the hypotenuse. And so they're going to be the same. So it's all satisfied. And then part C, second part, find all numbers C that satisfy the conclusion of Rolle's theorem. Okay, let's go ahead and do that one. So we have the derivative here, and so you just basically set that equal to 0. So we're looking at cosine of x over 2 equals 0. And we know that the cosine of pi over 2 is 0. So x equals pi is going to work. X equals pi will be the value that works. Okay, great. Any questions on that? I know I kind of went all over the place on the proof. Don't worry too much about that. Hopefully you'll understand a little bit. Okay, so number 2, I've copied down Rolle's theorem again, the antecedents and the conclusion. So if these are true, this is guaranteed. That's what that means. Okay, so number 2, f of x is 16 minus x to 2/3. F of negative 64 and f of 64. Okay, so let's do that over here. F of negative 64, that's going to be 16 minus negative 64 to the 2/3. So if we take the cube root first, then we get negative 4, and that's going to be a 16 minus 16, or 0. Okay, f of 64, that's 16 minus 64 to the 2/3, which is, you take the cube root first, that's going to be 4 squared, so that's 16 minus 16, that's also going to be 0. So they're both 0. Okay, so those values are both 0. That's the first 2 parts. Okay, now find all values in C such that the derivative is 0. Okay, if you take the derivative, okay, derivative of 16 is 0. Derivative of this part, you have a 2/3 coming down, and this drops by 1 power to negative 1/3. Okay, so essentially you have negative 2 over 3, and then x to the negative 1/3, that's the same as the cube root of x. Okay, so that's the derivative right here. And nowhere is this 0. Okay, so this doesn't exist. There is no place where the derivative is 0. Okay, no place where the derivative is 0. Okay, so if you look at this, this right here, these are both 0, right? That means that if you're looking at this interval from, if you're making this A and that B, then f of A is equal to f of B. That's true. It's also continuous on this closed interval. This function is, but where it doesn't work is this condition right here, differentiable, because f prime of 0 does not exist. Okay, so if you put a 0 for x, then that means that this is not satisfied. Okay, and then also, of course, the conclusion doesn't happen either because there's no place where the derivative is 0. Okay, so they're asking, what conclusions can be made? So they're kind of leading you into like a sort of a contradiction. Like they're kind of leading into like, oh, well, we satisfied A and C. Why can't we get this one here? We got 2 of the 3 properties. Why can't we get this based on that? And the answer is that's not guaranteed. You need all 3 of them in order to get this. If you had all 3 of them and you didn't have this, then that would be a contradiction. That would disprove Rolle's theorem. There wouldn't be such a theorem. Okay, but of course, So this first statement's wrong. This does not contradict Rolle's theorem because f prime of 0, no, that's not 0. This contradicts, no, it doesn't contradict. This does not contradict since f prime of 0 does not exist. And so f is not differentiable on negative 64 to 64. Okay, so this would be the correct answer right here. It does not contradict Rolle's theorem. Okay, that's kind of an interesting problem. Any questions about that? Okay, let's go on to the next one, number 3. And here we get into the mean value theorem. Okay, so mean value theorem, you have the same the first two conclusions are the same, but the third one is that there is a number c such that f prime of c is equal to f of b minus f of a over b minus a. Okay, now this right here, this is the slope of the line segment joining a, f of a, and b, f of b. Okay, so let me give you a picture of what this looks like. So here you could have a function like this. Maybe that's A and that's B. So with Rolle's theorem, these would have to be on the same horizontal line, but with the mean value theorem, this can be higher or lower than that one. Let's put it up here. Okay, so you have a function that is differentiable on this interval and continuous on the closed interval. So maybe it's something like this. Maybe something like that, okay? Now, this right here represents the slope of the line segment between these 2 points. Okay, so if we draw that line segment, I'll just do it with a dotted line. Oh, dang. Oops. Okay, so let's try again. Aim a little bit lower. Okay, there we go. Okay, so it says that there has to be a point where the derivative is equal to the line, and so maybe right here. Maybe the tangent right here, tangent to the curve is parallel to this line, and it's probably this is gonna have another one over here, by the way. You're just guaranteed at least one kind of such value. Okay, so this would be, these would be 2 different values of c that will work this. The derivative is equal to this right here. Okay, so I guaranteed at least one such point where the derivative is equal to this slope or this line right here. The way that this is proven, it comes really quickly from Rolle's theorem, and essentially you just do a little trick. You let h of x be equal to, so you have your f right on the interval from a to b. You let h of x be f of x minus f of a minus f of b minus f of a over b minus a times x minus a. Okay, and then so the first thing you do is you calculate this. H of a is, you put an a in here, this is going to be f of a minus f of a. That goes away. That goes away. So it's just going to be 0, right? And h of b, this is going to be f of b minus f of a, right? And this is going to be b minus a. Those will cancel. And you basically have f of b minus f of a minus f of b minus f of a. So that's also going to be 0. Okay, so H satisfies Rolle's theorem. Okay, it's going to satisfy these other two conditions just because it's like this is a first degree polynomial, and then this function satisfies that, and that's just a constant. So H is going to satisfy those two conditions. Plus, they're equal; those are equal to each other. So it satisfies Rolle's theorem. So that means that there exists a C in A to B such that H prime of C equals 0. Okay, and that means if you plug the C's in here, that means f prime of C minus 0. So just take the derivative of this. The derivative of this is f prime of C. The derivative of this is 0 because it's just a constant. Okay, after you plug the A in, you're just going to get a number. All of this is a constant, and this is x minus a. So the derivative of this is 1. So the derivative of this whole thing is f of b minus f of a over b minus a. And that's all got to be 0. The derivative is 0. And that means that f prime of c is equal to f of b minus f of a over b minus a. That's not a 1, that's an a. Which is the conclusion here, okay? So that's the proof of it. Let's do an exercise right here. Number 3. Does the function f of x equals natural log of x satisfy the hypotheses of the mean value theorem on the interval from 1 to 9? And the answer to that is going to be yes. Let me see here. So if I take the derivative of log x, I get 1 over x, right? And this is okay on the interval from 1 to 9. As long as x is greater than 0, as long as it's an interval that's got all positive numbers, then we're fine. It's differentiable and continuous. Okay. So this is true. Okay, so the second part, if it satisfies the hypotheses, find all numbers C that satisfy the conclusion of the mean value theorem. Okay, so all you need to do is calculate f of b minus f of a over b minus a. But we know that a is 1 and b is 9, right? So it's going to be, and then f is log, right? So it's going to be log of 9 minus log of 1 all over 9 minus 1. And log of 1 is 0, so that just goes away. So that means it's log 9 over 8. Okay, so we're looking for a value C such that f prime of C equals log 9 over 8. Okay, but we know that f prime of x is 1 over x, right? So that's going to be 1 over x is log 9 over 8, which means x is 8. Let me use the C there instead, okay? So C is 8 over log 9. Okay, like that. There we go. So that should work, 8 over log 9. Any questions about that? Okay, let's move to the next one, number 4. And what we're supposed to do here is show that this equation has exactly one real solution. Okay, so exactly one real solution. So the strategy in this sort of thing is, the way to do this is to show it has at least one solution. Excuse me. One solution. Okay, then show it can't have more than one. And then that means that, and that gives you exactly one real solution. So show it has at least one solution, and then show it can't have more than one. And the best way to do this one is this first one is the intermediate value theorem. Okay, so that's how we're going to start off with. Okay, so this is an equation. So we let f of x be that equation. Okay, so let f of x equals 8x plus cosine x. And then you start like plugging in values until you get this sort of thing, because you want to show that it's going to be it's going to be equal, that this expression is going to be 0, or you want to show this function is 0. Okay, so you start plugging in values, and what they've done here is that f of negative pi is negative 8 pi minus 1, which is negative, and f of 0 is 1, which is positive. Okay. So, so you have some value giving you a negative number and another value giving you a positive number. So because this is continuous, then by the intermediate value theorem, there has to be a number in between them that gives you 0. Okay. So let me see. Since f is the sum of polynomial and trigonometric function, f is continuous. So this statement is going to go into the third slot, because for the intermediate value theorem, you need it to be continuous. You don't need differentiable. That's interesting. It's differentiable, but you just need continuous. So it's okay to say more than what you need. Okay, and then if it's continuous and you have this condition happening, so let me draw a picture of this. So this is what this looks like. At negative pi, we're down here. Negative 8 pi minus 1. I mean, pretty far down here. At 0, you're up here at 1. Okay. So this function, to get from here to here, it's got to cross this x-axis. And where it crosses, it solves this equation. Okay. It solves that equation. It's a solution. And where it crosses. Okay, so this will be number 4. This second one. And then number 5 is this top one. Okay, so that is part 1, where we show that shows that it has at least one solution in here somewhere. We didn't need to find it. We just say, okay, how's the solution by the intermediate value theorem. And now, next part, we're going to show that it can't have more than one solution. And for this part, you're going to use the mean value theorem. Okay. let me back up a little bit, because this is going to be the second part. Let me back up. We'll go back to the, let me go back to the mean value theorem and explain something. Okay, so we've gone through the proof of this and everything, and then we've looked this, and they've got this problem right here that we're supposed to do. But it turns out that this stuff is fine for proving it and everything, and maybe that's the easiest way to do it, but it kind of misses most of the point of the mean value theorem by looking at it this way. The main point of the mean value theorem is if you look at it from, like, say, a different perspective. Okay, and that is this. If your derivative of your function is greater than 0, that means your function is increasing. Means it's increasing. If your derivative is less than 0, that means your function is decreasing. Okay, so I'm talking, and here with both of these statements, I'm talking about on an interval. Okay, and the reason for that is that if you take any 2 points on an interval, and let's say the derivative is increasing. Okay, if you had a value here and a value that's lower, that can't be, because there would have to be some place in here where the derivative is negative. Okay, because this slope of the slope of this tangent is negative. So there would have to be some place in here where the derivative would be negative. So if the derivative is positive, it has to be increasing. And likewise, you're going to have this right here. Okay. So hopefully that's a little bit of an explanation. And maybe this part will hit that through better. And so here we go. Suppose the equation has distinct real solutions a and b with a less than b, and f of a equals f of b equals 0. Okay, so here they're here to show that it can have more than one solution. You suppose that it has 2 solutions. Okay, and if you can get a contradiction, then that shows that it can have more than one solution. You suppose that it has 2 solutions. So usually this word right here, suppose, means that it's going to be a proof by contradiction. That you're actually supposing something that can't be, and you're going to show that it can't be, and then therefore it's not. Therefore they can't have more than one solution. Okay, so this first one, since f is continuous and differentiable, Rolle's theorem implies that there is a number r such that the derivative is 0. Okay, so that would be Rolle's theorem. If these 2 points give you the same value, they're both 0. That means they're equal to each other. If they're both zeros, if they're both solutions to this, if your 2 values are solutions to that, that means that the function f of a is equal to f of b. Okay, so Rolle's theorem says that there must be a point where the derivative is 0. Okay? So there exists an r such that f prime of r equals 0. Okay, but if you actually take the derivative, that will be in the third slot. If you take the derivative of this, the derivative that's a, the derivative that's negative sine r, right? So that's 8 minus sine r. And that's going to be greater than 0 because this is always between -1 and 1, and this is 8. So, you know, this is going to be at least 7. So that's going to be positive. And then that's a contradiction because here, this part here is saying that the derivative is positive everywhere. Here, it's saying the derivative is 0 at some point, which can't be. Okay, so this one right here goes in the last slot. This contradiction shows that the given equation can't have 2 distinct real solutions. So it has exactly 1 solution. Okay, let's look at number 5. If f of 4 is 9 and f prime of x is greater than or equal to 3, how small can f of 9 possibly be? Okay, so the derivative is greater than or equal to 3. So here's how you handle that one, or this one. Here you have 4, and f of 4 is 9. We'll put that at 9. That's a point on the graph. And we'll come over here to 9. The derivative is greater than or equal to 3. Okay, so if you draw a slope, a line with slope 3, then where is it going to intersect over here? Well, this distance is 5. So that's 9 plus 15, or 24. Okay, now if you have any point that's lower than that, then this slope will be less than 3. Any point that's lower than 24 on this vertical line will give you a slope that's less than 3. And that means that would contradict this. Because there would have to be some point in here where the derivative is less than 3. But the derivative is always greater than or equal to 3, so that can't happen. So this is the answer. So f of 9 has to be greater than or equal to 24.